Hi, I'm Jordan Baton from Limit State, and today I'll be explaining how to use the line structure component to define a line load in Peregrine, the structural optimization plugin for Grasshopper. The line structure component creates a line or line-based structure which can be loaded or used to represent a pre-existing structural component that can be utilized within the optimization process. The line input accepts a line defined in Grasshopper. The divisions input is an integer specifying how many equally sized divisions the line should be divided into for the purpose of applying load. The minimum area input is a floating point number describing the minimum cross-sectional area to ascribe to the elements. The move direction input is a vector describing the direction that the line element can move in. The default for this is 0, 0, 0, indicating no movement. The rigid input is a boolean. When set to true, the line element ignores the stress constraints defined in the material component. The bending capacity accepts all values between 0 and 1. A value of 0 assumes the line elements are rigid and cannot bend. A value of 1 assumes the bending capacity of each line is finite, calculated based on the available cross-section and present axial load. Bending capacity often isn't used in the optimal structure due to the relative inefficiency in load transmission. To create a line load, a line must be defined. The divisions input will control the locations of the discrete point loads representing the line load. The higher this number, the more accurate the solution will be. For this example, I'm not going to assign a minimum area. I'm going to allow the line to move in the y direction. This will be explained further once the solution is solved. I'm going to set the rigid boolean to false and have 0 bending capacity for this example. Now that the line structure component is set up, it can be connected into the line structure input to the line load component. This example applies a distributed force in the negative y direction. The line load is now connected into the load case component and then into the problem specification component. This is the solution post-geometry optimization, which is a smooth arch, with members acting purely in compression. This is the most efficient way to carry load. If the move direction input to the line structure component is set to 0, 0, 0, the line structure is now unable to move, and the optimum solution comprises of straight elements from each of the discrete load locations to the supports. Thanks for watching. For more information, visit our website.